Hello! In this video, we tackle a Robertson-Walker space-time problem. First, we compute the path of a light pulse emitted at the origin. Then, we calculate the proper distance between the origin and a point at a fixed universal time. Join us as we explore these fascinating aspects of our expanding universe. First of all, we have the Robertson-Walker metric, which is crucial for understanding the problem. This metric describes a homogeneous, isotropic expanding universe. In this video, we'll compute the path of a light pulse emitted from the origin and the proper distance to a point at a fixed time. Let's dive into the math. Now let's take a look at the Lagrangian. Using the Lagrangian density equation and the given metric, we can quickly derive the Lagrangian density. Essentially, the differentials of r, theta, and phi now become dr by ds, which translates to r dot, and so on, for theta and phi. For a better explanation, watch my previous video or ask me. I can provide a thorough explanation. Now, since the ray moves along theta equals pi over 2 and phi equals 0, the terms of the Lagrangian for theta and phi disappear. And since we are talking about a light ray, or null geodesics, we can set the Lagrangian to 0, thus getting the equation t dot squared minus e to the power of 2t over t sub h times r dot squared equals 0. This leads to the final expression in orange. Now, given the information from the problem, we set up the integral to solve for the path of the light ray. We integrate from the initial time t naught to time t, with the integrand being 1 over t tilde times e to the power of t tilde over t sub h. This is equal to the integral from 0 to r of t with respect to r tilde. Next, we need to work through these straightforward integrals carefully to avoid mistakes. We start from the initial time t naught to time t on the left side, and from 0 to r of t on the right side. After working through the integrals, we arrive at the final expression for the path of the light ray, negative t sub h times the quantity e to the power of negative t over t sub h minus e to the power of negative t naught over t sub h equals r of t. This equation describes how the distance r of t evolves over time in an expanding universe. Now, for the second part of the problem, we need to compute the proper distance. Using the equation delta s equals the integral of ds, which is also the integral of the square root of negative g sub mu nu dx mu dx nu, we can determine the proper distance between the origin and a point r greater than 0 along the line theta equals pi over 2 and phi equals 0 at a fixed universal time t. This involves integrating along the path in space-time while considering the metric tensor g sub mu nu. If you want to know what proper distance is in this particular case or have any doubts, let me know in the comments. Since we got null geodesics, we get the expression in purple. We realize that the term of the metric contributing to the integral in this particular problem is g nu of t equals e to the power of 2t over t sub h, the pink term on the screen. Then we got all the information to compute the proper distance using the following expression. D sub p of t and r equals the integral from 0 to r of the square root of g sub r of t dr, which simplifies to e to the power of t over t sub h times r. This means that as time increases, the factor e to the power of t over t sub h becomes larger, indicating that distances in the universe expand exponentially. This result highlights the effect of the universe's expansion on spatial distances, demonstrating how objects move farther apart at an accelerating rate as time progresses. This exponential growth is a key feature of cosmological models describing an expanding universe driven by factors such as dark energy. Thank you so much for watching. See you next time.